So it is, please, come and, sit.
Okay.
It is my pleasure to present Professor Nikolai Vasilevski from Mexico City,
Yes.
so from CINVESTAV, but, Center for Research and Advanced Studies. Okay. I should know this in Spanish, but I don't.
Centro de Investigación de Estudios Avanzados.
Muchas gracias. Okay. And with the Toeplitz operators on the Bergman space. Welcome.
Thank you very much. Well, for the first time, I will give a talk sitting on the chair. It's something strange experience, but it's much easier to manipulate with mouse.
Exactly. So you can actually point to the right,
Yeah.
the right direction.
They can hear us. I presume that since they're not complaining, they just maybe nod their heads. They can hear. Okay.
Oh, yeah, they can hear. They can hear us
Okay.
early in the morning, so
Okay.
we're good. Yes, thank you. Thanks.
Okay, so I'm sure that not everyone in this audience make Toeplitz operators every day, each day. So I will start from very general approach. Approach from the general operators here. So what do we have? We have a Hilbert space A. Then we have H naught, it's closed subspace. And then we have an orthogonal projection P from H to H naught. Then we take any bounded linear operator A, acting on a big space, so it can be represented in a 2 by 2 matrix is a direct sum decomposition H naught plus its orthogonal complement. Then, by definition, the Toeplitz operator, the symbol A, is nothing but the compression of an operator A onto subspace H naught. So we take an element from H naught, apply A, and project back to H naught. In matrix representation, in just this 1-1 entry. And the problem here, the question here, how do the properties of the operator A determine the properties of its compression? This is a question we address too. Well, we can define a bounded norm 1 linear operator, which sends any operator, bounded linear operator A, to its compression. And the bad things comes here. This operator has a huge kernel. This huge kernel basically says that we do not characterize exactly the property of compression, just looking for operator A, because we have the 3 extra entries which doesn't permit to do this. But fortunately, there are many important cases where I can do this. And one of these cases is related to Toeplitz operator. So let me pass to this setup. We will be doing everything on the Bergman space on the unit ball. First, we have unit ball in CN with obvious formula. And then for each weight parameter lambda from -1 to infinity, we introduce a family of probability measures. This constancy alpha is taken so that the volume of a unit ball is 1. Then we consider Hilbert space with this measure, and its subspace, the Bergman weighted space, this subspace of corresponding L2 on the ball with this measure, which consists of all functions being analytic on the unit ball. There is some special nice property of this Bergman space. First of all, it is a reproducing kernel Hilbert space, which means that there is a function reproducing kernel, which for x fits z is an analytic function belonging to the Bergman space, in such that evaluation functional various representation theorem is nothing but the scalar product of function with this reproducing kernel. This is the way how this reproducing kernel appears. And then we know that orthogonal Bergman projection from L2 to Hilbert space is just scalar product of function A with this reproducing kernel. Okay, now in our setup, big space, Hilbert space H is L2 with this probability measure over the unit ball. Small subspace H naught is the Bergman space, and projection P is the Bergman projection. a bounded linear operator acting on big space, we will take multiplication operator by L infinity function. That is the Toeplitz operator with symbol A. This function is nothing but the compression to the Bergman space over multiplication operator. Or we take analytic function, multiply by L infinity, it's not anymore analytic, it projects back to the Bergman space. What is known? It's known that if you would like to study properties of Toeplitz operator or algebra generated by them, it is sufficient to consider bounded uniformly continuous function. Algebra generated by Toeplitz operator with such symbol coincides with algebra generated by Toeplitz operator with infinity symbol. What is good and what is exciting, that in our case, this linear mapping from A to Toeplitz operator have zero kernel. So we can now ask, how do the properties of the operator A determine the properties of Toeplitz operator? There are some useful toolbox here. First of all, there is so-called weak symbol or Berezin transform, which is defined for all bounded linear operator acting on the Bergman space as follows. This is a function. So we need to take scalar product of operator A applied to function k small z times k small z, where k small of z is the normalized reproducing kernel. So k small of z has always norm 1. If you would like to define Berezin transform for Toeplitz operator, it is the same as the Berezin transform of function A. It's just this scalar product. Function A times zk, kz with kz. You see that I denote this mapping with parameter lambda. Why it is important? It is important because of so-called Berezin quantization. Berezin proposed a way to quantize function y operator acting on the Hilbert space, associating to a function A Toeplitz operator with this symbol. Physicists like H, like Planck constant. In analysis, it is the custom to use lambda. The relation between Planck constant and lambda is as follows. Alpha plus 2 is 1 over h. As in each quantization theory, there is a correspondence principle. That is, quantum should convert to classical when Planck constant tends to 0. In our case, lambda should tend to infinity. And the first statement of the correspondence principle is limit of the Berezin transform of Toeplitz operator is uniformly approached to the initial symbol when lambda tends to infinity. This converges in L infinity. What is important here, very important, then basically association to a function A Toeplitz operator is like one-way road. Having function I, A, you define a Toeplitz operator, but having Toeplitz operator, you can never recover function A. But this Berezin procedure permits us recover function A, like you need to take Berezin transform, send lambda to 0. This is the way how to recover initial C. Then this mapping lambda is obviously linear, but not multiplicative. And the second statement of correspondence principle says that it is asymptotically multiplicative. When lambda tends to infinity, the product TA TB is approaches to the product or to the Toeplitz operator of A times B. It's very important two properties, even if we will use them very much. Well, the next question. We would like to unhide the properties of Toeplitz operators studying their symbol, or unhide the properties of Toeplitz operator algebra generated by Toeplitz operator with a bunch of symbol A. Basically, what is bad? The Toeplitz operator generically never commute, but the symbol, of course, commutes, multiplication by a function. So one may have a curious question, whether or not one can find a class of symbols that generate just commuting Toeplitz operator. And unexpectedly, this question has answer yes. And what is, again, unexpectedly, that the key point here is the geometry of the underlying manifold. So the main point how to realize something in hyperbolic geometry of the unit ball. We start from the unit disk as a very simple and the most known case. So the unit disk, we can endow it with the classical hyperbolic method. And now we will do some geometry. What is geodesic? Everyone knows that geodesic in the unit disk is a part of an Euclidean circle or a straight line orthogonal to the boundary. Now, having two geodesics, L1 and L2, we can define some geometric object, one parameter family of geodesics, which are called pencil, determined by L1 and L2. So what do we have in our Euclidean world? Generically, two geodesics either parallel or intersect, nothing more. But in the hyperbolic geometry, there are three cases. We have a parabolic case with parallel geodesics tending to some point in infinity. We have elliptic intersecting geodesics in a point inside itself. And we have something strange, third case, disjoint geodesics with divergence in both directions. So this is a typical geometric cases in geometry, hyperbolic geometry of the unit disk. And these bold lines are called cycles. They are orthogonal trajectories to geodesics. They are known to be equidistance in Bergman metric. So say this distance in Bergman metric is exactly like this distance. And next slide is a mirror. So given any pencil of parabolic geodesics, consider the set of symbols which are constant on corresponding cycles. Then the Caesar algebra generated by Toeplitz operator with such symbols is commutative. So the moral is each pencil of hyperbolic geodesics generate a commutative Caesar algebra of Toeplitz operator. So the trick lies, the symbol should be constant on cycles, orthogonal trajectories to geodesics. And under some mild condition, any Caesar algebra generated by Toeplitz operator is commutative on each weighted Bergman space if and only if the generating symbol are constant on cycles of some pencil or hyperbolic geodesics. So basically, and this is if and only if result. There is another point of view on this based on group action. Möbius transformation are known to be movement on hyperbolic plane, and each Möbius transformation being parabolic, elliptic, or hyperbolic determine a certain pencil. Say for parabolic Möbius transformation, it is known that it has a double fixed point to the boundary. So we draw a pencil so the geodesics converge to this point. After that, what this hyperbolic Möbius transformation does, it moves any geodesics from this pencil to another geodesics. And if you generate one parameter group starting from this hyperbolic or either one in these three cases, Möbius transformation, and start with any geodesics, it recovers all geodesics from the pencil. Our cycles are here just the orbits, are the orbits of the action of this group. So we may say another formulation, consider any maximal one parameter, any, what is this? Enable.
Participant request live. Okay, just a second. Live, that means closed caption. Is that okay? It will recognize your voice and it's going to write. Okay.
Okay.
So, all right, let's give that a shot. Okay, so here we go.
You are director of this machinery. So well, so another formulation. Having any maximal commutative subgroup of Möbius transformation, consider symbols that are constant on orbits. Then the Caesar algebra generated by such symbol, Toeplitz operator with such symbol will be commutative. And this is exactly the way what we did with Raoul Quiroga sitting here to generalize the situation to the unit ball. To the unit ball, one needs to consider unbounded realization of the unit ball, this well-known unbounded Ziegel domain, defined as written this slide. We have first bunch of variable and the last one, and the point belongs to Ziegel domain if this restriction, if this property is satisfied. And as known, fortunately, that there are 5 different model groups of maximal abelian subgroup of biholomorphism of the unit ball. Quasi-elliptic, quasi-hyperbolic, quasi-parabolic, nilpotent, and quasi-nilpotent. The last one depends on the parameter k, which runs between 0 and then -1. If we count all together for dimension n, we will have n minus 2 different cases. So, okay, so this is the situation. So elliptic is just multiplication, is just n-dimensional torus, multiplication by coordinate. Quasi-parabolic is parabolic shift in last variable and action of torus. So this is a description of all this group. And the same mirror follows. Given any maximal commutative subgroup of biholomorphism of the unit ball, we introduce the set of symbols Sg of L infinity function that are invariant under the action of this group. Then the Caesar algebra generated by such Toeplitz operator is commutative on each weighted Bergman space for each values of parameters. What is very interesting and important, that for each such group, there exists an analog of the Bergman transform, unitary operator, given a real analysis realization of the Bergman space, such that the Toeplitz operator is unitary equivalent to some multiplication operator. Everything being unitary equivalent with multiplication operator obviously commute. This is the way how to prove this. One of the way how to prove this algebra is commutative. And this function, I would say spectral function, carries all the properties of main properties of Toeplitz operator. Toeplitz operator is bounded if and only if the function is bounded. Spectrum of Toeplitz operator is a closure of the image of this function, and so on and so forth. Let me give an example. Consider the two-ball and quasi-elliptic group, two-dimensional torus. So invariant symbol, it would be just symbol that depends on radial part of each variable, R1 and R2. Bergman transform this unitary operator maps unitarily Bergman space onto L2 sequence parameterized by 2 non-negative integers. And this spectral function, in this case spectral sequence is given by this formula. So these formulas have A, we have everything in this formula. Interesting question arises. We have maximal commutative subgroup. We have TG sister algebra generated by Toeplitz operator with invariant symbol. We denote by gamma G the sister algebra generated by corresponding spectral function. Of course, they're isometrically isomorphic. And the question is, can or cannot we characterize this function algebra, sister algebra, in some terms independent on Toeplitz operator? So we can say we have this algebra, this spectral function symbol belongs to this algebra. Okay, that is, it is a spectral function for some operator from that algebra. Unfortunately, the result known only for n equal to 1. This is really very challenging non-simple question. But in all three one-dimensional cases, the corresponding algebra coincide with the sister algebra of slow oscillating in certain sense function. For our quasi-elliptic case, radial case, this algebra is the sister algebra of slow oscillating sequences introduced by Schmid, exactly 100 years ago. He did it for absolutely another purpose, but this is, we may say that Toeplitz operator algebra is isometrically isomorphic to the sister algebra of slow oscillating sequences. What is interesting? This result does not depend on the weight parameter. And if you would like to study its compact of maximal ideal, it has this description. First of all, it's integers, z plus a fiber m infinity. Integers is very simple. This consists of all evaluation functional of sequence. First, second, third element of sequence, and so forth. Sequences are slow oscillating, so they have a bunch of partial limit at infinity. And this strange fiber, m infinity, collects all partial limits at infinity for all slow oscillating sequences. Neither of point of a m infinity can be reached by sequences. We need to use nets. What is interesting as well, that the above characterization remains valid for Toeplitz operator with jointly radial symbol acting on any unit ball and any symbol and any weight parameter lambda. Okay, this is a brief excursion to commutative algebra, and let us now go from commutative to non-commutative. Again, we will use some geometry. Consider maximal abelian subgroup G and its subgroup G0. And then we consider the class S G0 of symbols that are invariant under the action of the smallest group. Of course, this class is much wider than the class of symbol invariant under the bigger group. So the algebra will be much bigger and will not be commutative. What's the problem here? What are the properties of the corresponding non-commutative algebra and corresponding Toeplitz operator? Again, it's difficult and challenging question, which we started develop very recently. And what is known, basically, this simple example. Two-dimensional case, two ball, group, two-dimensional torus, subgroup, one-dimensional torus. But the trick is that this one-dimensional torus may act quite differently. How it works? Consider the pair kappa, K1, K2, where K1 is natural number, K2 integer, and the action of the group torus parameterized with this pair kappa is as follows. We multiply the first coordinate by t to the power k1, the second coordinate to the power t to the power k2. So they will act quite differently. And let me remind that the basis in this Bergman space is formed by normalized monomial. So we need to raise z to the power of 1, z2 to the power alpha 2 with alpha 1, alpha 2 from this set. What is interesting? So having this pair k1, k2, we introduce the subset of integer p, which are linear combination of k1, k2 with non-negative integer coefficients. And then, fixing this p, we consider the subspace of the Bergman space, which is closed span of all basis element alpha 1, alpha 2, such that p is linear combination of this alpha 1 and alpha 2 with k1 and k2. Then the whole Bergman space would be direct sum of all these subspaces when p runs through this set. What is important? Now, take any function a being invariant under the action of this group. Then the Toeplitz operator with this symbol leaves invariant all the subspaces in this direct sum decomposition. It's a great improvement. Instead of studying Toeplitz operator in the Bergman space, we need to study Toeplitz operator in all restriction on all invariant subspace and add something. It will be needed. We will consider three principal cases. How can I delete it? Oh yes. Kappa 1, 1, 1, 0, and 1 minus 1. This is picture for quite different invariant subspaces. For the case 1, 1, lambda 1 plus lambda 2 should be an integer. In all invariant subspaces is the not on these lines. All of them are finite dimensional. In the case kappa 1, 0, lambda 2 is 0, and lambda 1 can take, oh, sorry. Lambda 1 is 1, 2, 3, each one. And lambda 2 is any integer, so this is graphical representation of invariant subspaces. For the case 1 minus 1, the difference lambda 1 minus lambda 2 should be constant. So corresponding pairs lambda 1, lambda 2 lies on these oblique lines. So this is completely different description for invariant subspaces in these three different cases. It's not surprising that the corresponding algebra have completely different properties. And I will announce these properties, which we will consider later. In case 1, 1, all invariant subspaces are finite dimensional. All reducible representations are finite dimensional, and their dimension runs through all integers. All the projections onto invariant subspaces belongs to the algebra. In case 1, 0, all invariant subspaces are infinite dimensional. All reducible representations are either infinite dimensional or one dimensional. Again, all projection onto invariant subspaces belong to the algebra, which is not the case for the third. Although all invariant subspace again infinite dimensional, all reducible representation again are either infinite dimensional or one-dimensional, but drastically different from representation of the previous case. But surprisingly, none of the projections onto invariant subspace belongs to the algebra. This is differs from the previous case. In two previous cases, all projections do belong to the algebra. In the third case, none of them. Now let's consider briefly all of them. Case 1.1. This is our representation of the Bergman space onto the sum. Each subspace is a finite dimensional spanned by basis element with alpha 1 plus alpha 2 equal to p. It is p plus one dimensional space. We consider the sister algebra, which is generated by Toeplitz operator with a radial symbol r, and Toeplitz operator with this straight symbol phi k. Phi k, this is the point on the unit sphere. Passing to spherical coordinate is the spherical coordinate of the point z. Well, observe that our algebra contains all compact operators, in particular, or finite dimensional projection. Why it contains them? Well, because for radial cases, we know that corresponding sequences are slow oscillating. Projection has which sequences? 0, 0, 0, 1, 0, 0, 0. It's of course slowly oscillating sequence, so the element of the algebra. Now, all reducible representation are either representation of the intersection with compact operator or representation of the quotient algebra. Representation for each finite p is just all matrices, p plus 1, p plus 1. This is the restriction of Toeplitz operator onto this finite dimensional space. Representation, one-dimensional representation coming from the quotient. This algebra is just isomorphic to the algebra of continuous function of our famous n infinity, coming from this compact of maximal ideal, times closed disk centered in origin with radius 1/2. And this is how this representation acts on generators. This complete description of everything. Now, case 1.0. Again, we have this decomposition of the Bergman space onto infinite dimensional space. What is interesting here? That there is a unitary operator U that gives unitary equivalent representation. Each space HP is unitary equivalent to Bergman space with weight parameter p plus lambda plus 1 on the unit disk. So we have a direct sum decomposition of weighted Bergman spaces with different weight parameters. Please look carefully. P runs through all integers. So weight parameter tends to infinity. So we need, fortunately, we need meet Berezin quantization because something will happen as a limit. We consider invariant symbol under the action of the corresponding action of torus of this form. A is that strange combination of radial part, and B is vanishing oscillation on the boundary. I will explain right now what does it mean. This algebra of vanishing oscillation on the boundary and the unit disk consists of bounded continuous function such that if we consider hyperbolic disk of radius r centered in Z, consider any point W from this disk, consider variation on this disk, set Z to infinity, and this variation should be zero near the boundary, should vanishing oscillation near the boundary. And this algebra is known to be the maximal sister algebra, so that for all functions from this algebra, semi-commutator of Toeplitz operator are compact. Okay, for this symbol, one can easily verify that the Toeplitz operator with product AB is a product of TA, TB, or TB, TA, they commute. And after this unitary equivalence, in this direct sum of weighted Bergman spaces, Toeplitz operator with symbol A is just scalar operator in each weighted Bergman space with its corresponding spectral value. And the Toeplitz operator with symbol B is a Toeplitz operator with the same symbol B, but in differently weighted Bergman space. And this is the formula for this scalar value gamma. Very simple formula. Okay. So for each radial A, corresponding gamma are slowly oscillating sequence. So the sister algebra is isomorphically isometric to the set of slow oscillating symbol sequences. So each orthogonal projection does belong to this algebra. Compact of maximal ideal of this slowly oscillating, vanishing oscillating function, again, is D together with fiber on the boundary. D again, evaluation function on each point on the unit disk, and D is responsible for different limit values of oscillation function on the boundary. So now we consider sister algebra generated by this A and this B, Toeplitz operator with such symbols. Again, given any bounded operator T, which leaves all the subspaces invariant, there exists a bounded operator such that this Toeplitz operator is unitary equivalent to the restriction on two invariant subspaces. I will use this strange symbol like similar, not to write unitary operator. What is the result here? Each Toeplitz operator admits the following non-unique representation. There's the Toeplitz operator with the same symbol C on differently weighted Bergman space plus compact operator. This symbol C uniquely defined on this set and can be arbitrarily extended by continuity to the rest of its domain. And Toeplitz and compact operator tends to zero in norm when P tends to infinity. Okay, first of all, this is somehow the impact of the Berezin quantization procedure. We take any point, limit point of this set M infinity. So there is a net P beta which converges to that point. Then we consider Berezin symbol of our Toeplitz operator with weight which corresponds to this net, and limit by net tends to infinity. And we will end up with slowly, or with vanishing oscillating function on the compact of maximal ideal. So now we can characterize all reducible representation. First of all, we have infinite dimensional representation, which send each Toeplitz operator to its restriction onto the corresponding level, onto the corresponding invariant subspace. Then one-dimensional representation, first we restrict to corresponding level, and then we consider Fredholm symbol. quotient and fix the point of its domain. And the last one is exactly connect with this quantization procedure. We fixed point into this M infinity. We fixed zeta in the compact of maximal ideal of the vanishing oscillation set. Then we send Toeplitz operator why this procedure first to corresponding slowly oscillating vanishing oscillating function, and then we fix arguments. This is the list of all irreducible representations. More sophisticated case, 1 minus 1. Here is a direct sum decomposition where each infinite dimensional invariant subspace is a closure of linear span of each basis vector, so that the difference between alpha 1 and alpha 2 is equal to P. And we consider this as our algebra, which is generated by Toeplitz operator with radial symbols, which are L infinity on the base of the unit ball considered as a Reinhardt domain, this domain where R1, R2 belong, and the Toeplitz operator with the symbol T1 times T2 to the power n, where this is angular coordinate of the corresponding Z1 and Z2. It's very easy for this radial symbol. We already saw this spectral sequence. And what we do, we just introduce some notation related to any invariant subspace. Alpha 1 and alpha 2 have a difference P, so we denote E tilde NP, this basis element whose alpha 1 and alpha 2 differs by P. And this would be the element of the sequence for the corresponding basis element. So this is just to simplify. We simplify just to have one parameter basis on each invariant subspace and one parameter spectral sequence. Then, first of all, it can be proved that this spectral sequence again slowly oscillating in our sense. And what is important, that the restriction for different invariant subspaces of these slowly oscillating sequences to the set M infinity is the same, which in particular implies that none of the projection belongs to this algebra, because if we have projection, it should be 1 for projection and 0 for logic, but they have the same restriction. And Toeplitz operator with this symbol restricted to the invariant subspaces is unitary equivalent to its spectral sequence. What is going on with Toeplitz operator with the symbol? It acts on basis element as a weighted shift operator. We shift by m elements, and this is the formula for weight, which of course depends on P, invariant subspaces. What is important for each P, the limit of the weight sequence is 1 at infinity. That implies in particular that this operator is nothing but m's power of the standard right unilateral shift plus a compact operator. 3. So let us fix invariant subspace at the node T with this P, the unit of algebra generated by our Toeplitz operator. This algebra contains an ideal of compact operator. Few minutes.
Yes.
Few minutes, maybe 1 or 25.
No. 2 minutes, somewhere between 1 and
between 1 and 3. Okay, great. So, well, so this is weight. This is weight. This is description, maybe not important. So we have a description on each level. Then we would like to combine the description on all levels. What we will have the different story. If we identify each level with a standard L2 space, then the Toeplitz operator will act differently. Weights for shifts will tend to the same sequence which has limit 1. So this is exactly the unilateral weighted shift for each level. But with radial function, it's quite different. Each level we have a sequence. These sequences do not have limits in plus and minus infinity. They square root slowly oscillating. What's that? Well, this is the meaning of the square root slowly oscillating, which implies additional compactification. For this, so we have one compactification by Bergman quantization, another with a square root compactification, which permit us to describe all reducible representation. That's it. Thank you very much.
Are there any questions from the audience here or from the audience online?
Do you consider other domains than just the ball, unit ball?
Well, yeah, we consider this Raoul just Reinhardt domains, and this Raoul, Matthew, and Gester considered bounded symmetric domains. The difference, big difference, bounded symmetrical domains have bigger than one rank. So maximal Abelian subgroup doesn't work.
A rank is bigger than 1.
Rank is bigger than 1. So there is another results and another instruments based on representation theory.
But you don't know the automorphisms on the right-hand domains and this.
No, they have a lot of stuff, but there are many unsolved questions so far.
What is the situation of polydisk? Is it some?
Polydisk is not interesting because, you know, Bergman space is just tensor product. So you just tensor one-dimensional results.
Mm-hmm.
That's it. It's important to consider irreducible domains.
So I guess in the case of the disk, for the radial Toeplitz operators, you have these slowly oscillating sequences that come out. What happens? What is the result then? Do you have one for the nilpotent and hyperbolic cases where you have a continuous spectrum? Is there an analogous result there?
Well, there's together with Roy, we got spectral function for all these cases for the ball, but no more. You know, it just started questions.
I think he meant the vertical case. You have slowly oscillating functions in that case, right?
No. For unit disk, yes. For parabolic and hyperbolic, it's again slowly oscillating function in different sense.
Okay.
For one-dimensional case, there are complete description.
That's what I meant in the one-dimensional case.
For one-dimensional
so instead
case,
of slowly oscillating sequences,
yes, complete answer. For the multidimensional case, so far no. Because you know you have too many directions. It should be something very complicated. You can approach to infinity in many different ways.
So are there any other questions from our friends that are online? Okay. Any other questions from the room? So, well, I think then, thank you so very much for watching.
Thank you.